Titanoboa wasn't just the largest snake that ever lived. It was the longest, cold-blooded predator that has ever crawled on this planet. Longer than a school bus, heavier than a grizzly bear, thick enough at the middle that you couldn't wrap your arms around it. And the only reason it could exist at all is that the world it lived in was so unbearably hot that nothing about it should let you sleep easy. 60 million years ago, in a flooded jungle in what is now northern Colombia, the apex predator of South America was a snake that ate crocodiles whole. And the only reason we know it ever existed is because somebody noticed a strangely large bone in a coal mine and labeled it wrong. This is the story of an animal so improbable that the first paleontologists who looked at it assumed they were holding a mistake. It's the story of a tropical climate that would cook a modern human in a few days, an ecosystem of giants, and a predator that ruled the swamps for the better part of 1,000,000 years. And before we're done, we'll come back to one uncomfortable question. The world that made Titanoboa possible is the same world climate scientists are watching the modern Earth slowly drift back toward. To understand Titanoboa, you need to understand the moment it arrived. The dinosaurs had been gone for about 6 million years. The asteroid had hit, the fires had burned, the skies had cleared, and life had spent the intervening millennia rebuilding itself into something almost unrecognizable. The tropics didn't bounce back as a green paradise. They bounced back as a furnace. Year-round equatorial temperatures stayed in a band that modern humans cannot tolerate without air conditioning. Daytime peaks in the swamps of what is now Colombia regularly cleared 100 degrees Fahrenheit, with humidity that would make a Florida summer feel like a desert. There were no ice caps anywhere on the planet. Sea levels were higher. The Atlantic Ocean was narrower. South America was still drifting slowly away from Africa, and the giant landmass between them was a tangle of rivers, swamps, and floodplains where nothing grew small. That's the key word. Nothing in Cherrejon, pronounced Serre-hon, grew small. The turtles were the size of breakfast tables. The crocodiles were 15 to 20 feet long. The lungfish were nearly as long as a person is tall. The plants were the ancestors of modern rainforest giants, and they were already enormous. And presiding over all of it, sliding through the warm brown water, was the snake. The discovery itself is one of those stories that sounds too convenient to be true. In the early 1990s, an open-pit coal mine in northern Colombia called Cerrejón started exposing rock layers from the Paleocene. Cerrejón is enormous, one of the largest open-pit mines in Latin America, big enough that you can see it from orbit. As the diggers scraped away modern Earth to get to the coal underneath, they were also scraping away 60-million-year-old sediment. And inside that sediment were bones nobody expected to find. In 1994, a Colombian geologist working at the mine, Henry Garcia, noticed something odd embedded in the rock. He didn't know what he was looking at. He labeled it a petrified branch and slid it into a display case at the coal company's office. There, it sat for nearly a decade. The fossil almost died there, quietly, behind glass, on a forgotten shelf, in a building most paleontologists had no reason to visit. What saved it was a separate discovery almost 10 years later. In 2003, a Colombian geology student named Fabiani Herrera found a layer of fossilized plant leaves nearby and showed them to a paleobotanist named Carlos Jaramillo, who worked with the Smithsonian Tropical Research Institute. Jaramillo called in Scott Wing, the Smithsonian's curator of fossil plants. And Wing, walking past Garcia's display case on a tour of the office, stopped and pulled the petrified branch off the shelf. It wasn't a branch. Wing sent a photograph of it to a paleontologist at the University of Florida named Jonathan Bloch. Bloch's first guess wasn't a snake either. He thought he was looking at a piece of a land animal's jawbone, maybe a dinosaur, an ancient crocodile relative that lived in this exact swamp. The shape was wrong for any snake on record. The dimensions were closer to the spine of something that should have had legs. He brought in colleagues. He compared the bone against reference specimens from every large reptile group anyone could think of. Nothing else fit. The geometry was unmistakably Ophidian. It was a snake. The bone just shouldn't have been that big. A formal expedition followed. Researchers from the University of Florida and the Smithsonian went back to Cerrejón and started pulling more bones out of the coal seams. Vertebrae, ribs, more vertebrae. The mine workers, once they understood what was happening, started flagging strange fossils as they uncovered them. The bones came out of the ground in batches, washed clean by the equipment, embedded in chunks of black coal. By 2009, when the team finally published the paper in the journal Nature, they had pieces of at least 28 individual animals, different sizes, different ages, enough to confirm that the giant wasn't a one-off freak. It was a species, an entire population, a breeding line of monsters that had ruled this swamp for 1,000,000 years. The size estimate itself is worth pausing on because it's one of those numbers people assume came from some kind of dramatic full skeleton reveal. It didn't. There is no complete Titanoboa skeleton in any museum on Earth. There never has been. What exists are vertebrae, mostly, and a few partial skulls. The size estimate was reverse engineered from a single ratio that holds true for almost every snake alive today. The width of a single vertebra correlates predictably with the total length of the animal. If you measure the bone, you can calculate the snake. So they measured, and they calculated, and they triple-checked the number because the answer kept coming back wrong. Length, somewhere between 42 and 50 feet from snout to tail tip. Most estimates land around 42 feet, which is roughly the length of a city bus. Some specimens may have stretched closer to 50, which is longer than a greyhound. Weight, about 2,500 pounds. That's more than a fully grown grizzly bear, more than a dozen adult men combined. About the weight of a Mini Cooper. But the number that really gets to people isn't the length or the weight, it's the diameter. At the thickest point of its body, Titanoboa was over 3 feet wide. If you laid one out on the floor of an average American living room, its body would block a doorway. If it raised its head off the ground, the head would meet you at the eye level of a standing adult, not coiled, just lying there. 3 feet thick, 40+ feet long. For comparison, the largest snake alive today, the green anaconda, tops out at around 20 feet and 500 pounds. Titanoboa was more than twice as long and 5 times as heavy. The gap between Titanoboa and the modern anaconda is bigger than the gap between an adult human and a kindergartner. Now, picture standing in that swamp. The water is warm, somewhere around bathtub temperature. The air smells like wet vegetation, rotting wood, and something organic and faintly meaty that you can't quite identify. The water comes up to your chest. You can't see your own feet. The bottom is mud and decomposing plants. Everything around you is moving. Crocodiles slide between cypress roots. A turtle the size of your dinner table drifts past. A lungfish nearly as long as you are tall slips past your knee and disappears. Then you feel the current change. Titanoboa didn't hunt the way most people imagine. The picture in your head, the tree branch ambush or the slow movie villain slither through high grass, is wrong. The hunting style of the largest snake that ever lived was the hunting style of a modern anaconda, scaled up to a size that breaks the brain. It lived in water, almost entirely. The water held its weight, which mattered because at 2,500 pounds, moving on land was slow and energetically expensive. In water, it became something else entirely. Quiet, buoyant, patient. The current change was you not seeing it. Titanoboa would lie just below the surface, often with only its eyes and nostrils above the waterline, blending into the leaf litter and mud the color of weak coffee. By the time you noticed something was wrong, it was already on you. There would be no warning bow wave, no shadow under the water, no sound. Modern anaconda attacks on humans, when they happen, follow the same script. The victim doesn't see anything. They feel a sudden pressure on a leg, a torso, a neck. Then the world tips, and they're being pulled under. Where an anaconda strike pulls a 150-pound human off a riverbank, a Titanoboa strike would have pulled a full-grown crocodile out of an ambush position. The math of the struggle would have been over before it began. What it ate took longer to figure out than the size did, because for a long time, scientists assumed Titanoboa was doing what big snakes do, constricting large mammals, wrapping a hapless prey item and squeezing until the cardiovascular system gave out. That theory held for years. Then somebody actually looked at the skull bones, and the diet started to look very different. In follow-up studies after the 2009 paper, paleontologists analyzed the few cranial fragments they had, including jaw structure and tooth attachment points. Titanoboa's teeth were small, sharp, numerous, and arranged in a pattern almost identical to modern fish-eating snakes. The shape of the jaw suggested a hunter that grabbed prey and swallowed it whole, rather than wrapping and crushing it. The mouth could open wider than a manhole cover. That doesn't mean Titanoboa never ate crocodiles. It almost certainly did. Cerrejon was home to a 15-foot dinosaur called Acherontissuchus, pronounced Acherontisocus, as well as a smaller dinosaur called Cerrejonosuchus that maxed out around 7 feet. Both were the right size to end up inside a Titanoboa. The relationship probably ran both ways. Adult Titanoboa likely ate the small and mid-sized crocodile relatives. The larger crocodile relatives, in turn, may have hunted juvenile Titanoboa when the snakes were small enough to lose a fight. But for the adults, the bulk of the diet was probably big fish, giant lungfish, catfish the size of a kayak, things that lived in the water with it and didn't have time to escape when the warm current shifted. When a Titanoboa did manage to swallow something the size of a small crocodile, the meal didn't end there. Snakes don't chew, they digest. A modern anaconda that swallows a capybara can spend a week or longer breaking it down internally. Mostly immobile, mostly hidden, mostly defenseless. Scale that up. A Titanoboa that ate an Acherontissuchus would have been a 2,500-pound predator with a visible bulge somewhere along its body, lying in shallow water, digesting at the speed of geology. For days at a time, the apex predator of the Cerrejon swamp would have been completely vulnerable. The only thing in the ecosystem big enough to threaten a digesting Titanoboa was another Titanoboa. And we don't have direct evidence of cannibalism in the species, but we don't have evidence against it either. In the small group of large modern snakes that live alone, eating your own kind when you find one helpless is biologically a sensible move, all of which leaves one question to answer. Why was Titanoboa even possible? Snakes are cold-blooded. Reptiles, in general, depend on their environment for body heat. The bigger a cold-blooded animal gets, the more efficient its body becomes at retaining that heat. But there's a trade-off. Big bodies also need more heat to operate. There's a known relationship in modern biology between the maximum body size of a cold-blooded predator and the average temperature of its environment. Run the math forward for Titanoboa, and you get an inescapable conclusion. The world it lived in had to be brutally, relentlessly hot. Average temperatures in tropical Colombia 60 million years ago landed in a band between 86 and 93 degrees Fahrenheit, around the clock, year-round. Modern Cartagena, just up the coast, averages about 82 degrees. A 6 to 10 degree difference doesn't sound dramatic, but it's the difference between a snake that maxes out at 20 feet and a snake that maxes out at 45. And the modern relevance lives in that math. The warm window that produced Titanoboa was the build-up to one of the most studied climate events in Earth's history, the Paleocene-Eocene thermal maximum, which hit about 56 million years ago. A few million years after the last Titanoboa bones were laid down, the planet ran an even hotter experiment on itself. Carbon released into the atmosphere, tropical temperatures climbing further still, polar ice gone, ocean chemistry shifting. The PETM is one of the closest analogues we have to certain projections of modern climate change. It took the planet about 200,000 years to recover from that event. 200,000 years. As a comparison, modern humans, our entire species in our current form, have existed for about 300,000 years. The recovery from one heat pulse took longer than we have been around to remember it. I'm not going to tell you what to do with that information. The math is what the math is. Titanoboa was not alone in this swamp. The fossil record at Cerrejón is unusually well preserved, which means we have a relatively complete picture of the apex predator's neighborhood. And the neighborhood was a horror show. There was Carbonemes, pronounced Carbonemis, a turtle with a shell more than 5 feet across and jaws strong enough to crack the bones of small crocodiles. There was the previously mentioned Acherontosuchus, the 15-foot crocodile relative that lived in the same waters. There were giant lungfish the length of a paddleboard, eel-like creatures over 6 feet long, and ferns and palms that would have closed in around any path through the swamp until you couldn't tell where the trees ended and the water began. If you dropped a modern human into that environment, the snake might be the least of your problems for the first half hour. The heat would get you first, then the dehydration, then the insects, because the Paleocene tropics had insects we don't fully understand, since most of them didn't fossilize. After that, it's a roll of the dice. Crocodile, turtle, snake, lungfish, something with teeth and patience and a body plan that has had 60 million years to be forgotten. There's a detail in the Cerrejón fossil record that doesn't get enough attention. The crocodilians and Titanoboa show up in the same coal seams, often only feet apart. Some turtle shells from the formation also show bite marks, though the marks have been attributed mostly to the local crocodilians, not the snake. What the fossil record makes obvious is the size hierarchy. The largest snake the world has ever seen, sharing a swamp with the largest turtles and crocodile relatives of the Paleocene. And only one of those animals was big enough to top the food chain. The swamp is gone. The bones aren't. Titanoboa existed for roughly 1 million years, maybe more. The species is only known from the Cerrejón Formation in Colombia. After that geological window, the bones go quiet. What we know is that the world that eventually followed was, slowly, a cooler one. Polar ice returned, temperature gradients between equator and pole rebuilt, and the math of body size shifted. Generation after generation, the upper limit of viable snake mass dropped because the largest individuals could no longer absorb enough heat from a cooler environment to digest their food fast enough to survive. The species didn't die in a catastrophe. It got smaller and smaller until eventually what was left wasn't Titanoboa anymore. It was something more familiar. What survived was Titanoboa's smaller cousins. Modern boas, modern anacondas, modern pythons, each one a descendant of the same lineage that produced the largest snake to ever exist. You can see the family resemblance if you look for it. A green anaconda is a Titanoboa with the volume turned down. Same body plan, same hunting style, same patience, just smaller because the world that allowed for the giant version doesn't exist anymore. For now, here is what stays with me about Titanoboa. The size is incredible, but you can pull up a chart. The diet is striking, but plenty of predators have eaten other predators. The thing that gets under my skin is the fact that this animal existed because of conditions, not despite them. Titanoboa did not claw its way to the top of the food chain. It was placed there by an unusually hot, unusually wet, unusually green window of Earth's history. When that window closed, the largest snake the planet had ever produced wasn't outcompeted and wasn't hunted to extinction. It simply could no longer exist. The biology that made it possible required a climate the Earth no longer had. That's the thing about life on this planet. Monsters are not impossible. They are conditional. The right temperature, the right swamp, the the right amount of carbon in the atmosphere, and you get a snake the length of a city bus. The wrong combination, and that snake never appears. The Earth is not a stable backdrop where predators evolve to fill fixed roles. The Earth is the protagonist. What it gives, it can take back. And what it once allowed, it could allow again. 60 million years ago, the tropics of what is now Colombia were the home of the largest snake that ever lived. The bones are still there, buried under the coal. Cerrejón is still an active mining operation. Paleontologists are still working the site, and every few years another vertebra, another rib, another fragment surfaces from a coal seam that nobody had touched yet. The total number of confirmed Titanoboa individuals keeps climbing. The species existed in larger numbers than anyone first guessed. The swamp was not home to one giant. It was home to a population of them. A breeding ecosystem of monsters that has left its bones inside the rock and is, slowly, one specimen at a time, being put back on a museum shelf. The recipe is still on the shelf. It's just the temperature, mostly, that's been off. Thanks for watching, and I'll see you in the next one.